Hello, everybody. Welcome to my lecture today. We would like to talk about exploring computational thinking in the context of computing education. I am from Lithuania, Professor Valentina Dagienė. I would like to introduce myself a bit. My interest is in computer science education, informatics curricula for schools, Olympiads in informatics, gamification, puzzle-based learning, intelligent technologies for education. More about me you can find in the link below. Also, I am writing papers, books. I'm editor of 2 international journals. Also, I established a challenge on informatics and computational thinking, BEBRAS. My talk today will be about briefly about Lithuania and Vilnius University, then about terminology of computational thinking, about categories and components of computational thinking, then a relation between computational thinking and programming and computational thinking across the curricula. Then we will talk about automatable solutions, learning and teaching computational thinking, and at the end I will present a little bit about BEBRAS and BEBRAS tasks. Lithuania. Lithuania is a small country in the middle of Europe, and we have population around 3 millions, a little less than 3 millions. I'm from Vilnius. Vilnius is capital city. We have a little more than 500,000 inhabitants. Our currency is euro, because we are in Europe Union. And you can see here in map our borders that are our neighbor countries. Vilnius University are located in capital city in Vilnius. You see that Vilnius is a nice old city, and our university has long history. As you see, Vilnius University established in 1579. But of course, we have many modern equipments, and campus. Vilnius University is spread in several campuses around Vilnius. Vilnius University is number 1 in Lithuania, and between 400 and 410 according QS World University Rankings. We have more than 20,000 students, bachelor and master degree. Also, we have doctoral students, and they are spread in 29 fields. Now we will talk about computational thinking. Terminology. Terminology is still confusing. There are many papers written about computational thinking during the last 10 to 15 years. But I would like to present a few definitions from the Royal Society, published in 2012, and now it is slightly renewed. They made this some slightly difference between computing. Of course, computing is a broad subject area, roughly equivalent to what is called ICT in schools and the IT in industry, as a term is generally used. That's why we need, when we are talking about universities and schools, we need to talk about computing education. Computer science is a rigorous academic discipline encompassing programming languages, data structures, algorithms, and some other fields. Information technology is mainly about using computers and other devices. Digital literacy also is like equivalent information technology, but now we started more and more use this more general term, digital technology. I would like to mention a very interesting paper. Marie Webb and his co-authors wrote 4 years ago a paper that presented broad definitions of all computer science or informatics, and also paid attention on curricula in K-12 school. And here we can find very very well polished, edited definitions of computing, of programming, also of digital research and computer science. So mainly in my presentation and in many papers, computer science, informatics, and computing education, all these are almost similar terminology. And when I'm using informatics, it means like the same like computer science or computing education. What is computing education? According UK curriculum, the national curriculum in England framework, this computing education is highly quality computing education equips pupils to use computational thinking and creativity to understand and change the world. Actually, computing education is mainly used in England. So before starting more going deep in computational thinking, I'm showing this slide, that schema, that about why we need to talk about computational thinking, because we are talking also about several stages of industrial revolution, World Economical Forum, and now we are on the, as you see on the right side, that we are searching talent pupils. And we need to teach them computer science. We need to teach deep understanding of our technology. Another schema also is disciplinarity. About we need to talk about disciplinarity of different subjects and integration CT with STEM. So I will talk later about integration computational thinking with STEM and with other engineering disciplines. Computational thinking started from Seymour Papert. He mentioned in his very challenging book, Mindstorms, Children, Computers, and Powerful Ideas. So here you see that my last photo with Papert when we had a conference in Hanoi, Vietnam in 2006. In 2006, Janette Wing popularized this term computational thinking, and she wrote several papers, well-known papers that many people cite. These papers, what computational thinking is, that she focused on solving problems, designing systems, and understanding human behavior. Later, she wrote about that computational thinking is a thought processes involved in formulating problems and their solutions, so that solutions are represented in forms that can be effectively carried out by an information processing agent. You see that there is also some additional that computer or computational agent involved in her definition. Before we need to start from some history of computing, and one of the most prominent work is from David Harrell, Algorithmics, the Spirit of Computing. And in his book, he explains three complexities of computational complexity, behavioral complexity, and cognitive complexity. Computational thinking is not thinking like a computer, it is thinking like a computer scientist. So this quotation became from many researchers in this field. Donald Knuth mentions that this is computational thinking is a special way of thinking. The people who got interested in computers started to realize that their way of thinking was shared by others, so they began to congregate in places where they could have people like themselves to work with this. This is how computer science came to exist. Now we are going more deep to understand what is computational thinking, and Despite an intensive research history of around 15 years of computational thinking field, researchers have not reach a consensus on the definition of computational thinking. And I think maybe it is not necessary to have precise definition, as we do not have, for example, algorithm definition or just other very common used terms. We need to understand, it means we need to look at computational thinking from different angles to discuss more, and then to understand by doing, by learning, by discussing. So CT can be understood as a way of thinking used to develop solutions in a form that allows executing those solutions. This is very important. An executor can be a computational agent, for example, like computer or robot, and that should be guaranteed that results should be achieved by doing them automatically. I put there some also from papers that you can Google quite easy and found these interesting papers. So, however, they all these authors specify that it is not just problem solving. The solution of problem must be expressed in a way that allows a computational agent to solve. One very interesting report launched by European Union in 2016. Maybe you can say that it's a little older because it's 5 years, but now we are working. I'm involved also in this team to work to produce new report, and will come in January next year, on developing computational thinking in compulsory education. This is mainly about computational thinking in schools, and more specific in compulsory education. So in this report, there is a computational thinking model presented, consisted of four components, as you see here from this schema, that include many items of, like, for example, integration of computational thinking in curricula, placement also in curricula, assessment, also support international exchanges, stakeholders, grassroots, some initiatives, and you can read more about this model in publications that I've put a link below. Maybe it is interesting to see computational thinking relations with other terminology. This graph presents that computational thinking, of course, is very tightly related to computer science, to algorithmic thinking, to information literacy, of course, problem solving. There is another another representation of computational thinking relation with other terminologies or other subjects or part of subjects. Computational thinking can be understood also as a competence. For example, here from several papers like Barr Harrison, Woolrad, and Weintraub, there is also some they indicated that computational thinking is characterized by skills, also by attitudes. And we can categorize definitions. What is really important when we would like to understand better computational thinking, these categories can help us to do so. The three categories can be summarized. The first one is generic definition. It's that focus mainly on thought process. Second one category is about operational or model definition. that described what CT entails based on fundamental elements. And the third one is with focus on educational and curricular definitions derived from different frameworks. Different authors present different frameworks, and there we can see that focus on problem-solving methods or understanding of concepts of thinking computationally means like being able to approach and solve problems efficiency. And there are some other also frameworks can be involved. Here in this table, I put the same three categories, but with some examples from analyzed literature and some also indication to these authors that can be read, and really it is interesting to observe how this understanding of computational thinking is going from different viewpoints and wider and deeper. Another thing to pay attention when we are talking about computational thinking is concepts. So there are plenty of concepts involved in computational thinking, and so concepts related to generic problem solving can be here. I listed several of them, like abstraction, data analysis, data collection, data representation, decomposition, and so on. Other concepts can be related to programming and computing. Some of them are, of course, it's repeated like in generic problem solving. We have in this part we have algorithm design, automation, Boolean logic, data types, events, and more like very specific like functions, loops. Also some broader like algorithmic thinking, and still there are some discussions about what is relations between algorithmic thinking and computational thinking. So this the most key components used in literature are 4 or 5 or 6 approximately. Here you see 4 components: is algorithm, decomposition, pattern recognition, and abstraction. I would like to add one more, like automation, what is very, very important. Of course, some authors combine automation together with algorithms. What about computational thinking and programming? There are many papers that are written about this relation between programming and computational thinking, that they are deeply intertwined. A dual association between CT and programming is noticed. Programming supports the development of CT, while CT provides to programming a new updated role. The distinction between computational thinking and programming is subtle in principle. CT does not require programming at all, also in practice. Representing a solution to a problem as a program provides a perfect way to evaluate the solution, as a computer will execute the instruction to the letter, forcing the student to refine the solution so that it is very precise. This is a quotation from the same Merriweb paper that I mentioned before. So CT is not necessarily about programming, but rather the emphasis is on problem solving, which promotes learning experiences, summarized by Hassan and his co-authors. Simon Peyton-Jones asked question, why coding matters? And in his blogs, there are several interesting discussions. One of them, he told that coding is not the message of the new computing curriculum. It is a medium. Coding is a lab work of computer science. It motivates, illuminates, and brings to life the dry bones of theory. Without programming, computer science would be dry, theoretically husk of a subject. Programming develops thinking. Seymour Papert wrote in 1980s in his book that I mentioned before, Mindstorm: Children, Computers, and Powerful Ideas. He wrote, I began to see how children who had learned to program computers could use very concrete computer models to think about thinking and to learn about learning, and in doing so, enhance their powers as psychologists and as epistemologists. The new book, quite new book, published in 2019 from Peter Denning and Matti Tedre, Computational Thinking. So there are like short history of computing, computer science, and the connection to computational thinking. What is the most important that Denning and Tedre, they wrote that computational thinking compromises the mental skills and practices for, first one, designing computations that get computers to do job for us, and explaining and interpreting the world as a complex of information processes. But the most important is that they came to conclusions that development of computational thinking has opened computing education. And now we see this process going in European countries, that almost all European countries are establishing computer science, informatics, or computing education in compulsory education. The same in Asia countries. That means that this is the subject computer science is very important to start to teach students in early age. And computational thinking is in computer science or inside or integrated with computer science informatics curricula. Now we will move on to main ways of implementing of computational thinking. Like I would say that zero level is applying the approaches of computer science to problems in other disciplines. And level one, higher level, is finding automatable solutions to problems. And now my presentation mostly will focus on these two levels. The first one is more like Jonathan Wing wrote, that more universally applicable. And we already talked about definitions from Jonathan Wing, but I should add one more, that informally computational thinking describes the mental activity in formulating a problem to admit a computational solution. For Selby and Woolard about computational thinking, they produced this table with some terms, status, and justification when we are talking about the definition of computational thinking. A well-known schema that I took from Barefoot Computing from England. This is, as you see, this is already this schema established in 2014, but still many authors are using that, because there is on one side we can talk about concepts, and on other side we can talk about approaches. Approaches is very important also to when we are talking about computational thinking, so tinkering, creating, debugging, perceiving, and collaborating. That I would like to introduce a very short task for small children that is taken from the same Barefoot England. Something like draw a triangle body. This is algorithm. Add 3 eyes, add 3 wings, add 3 legs, add a tail, and algorithm making steps and rules. And what we can get, if we give to children, we can get different figures, different pictures, and we can discuss why children painted differently, or this is introduction to algorithms, and it is really nice, simple algorithms that just 5 years old children can do. Now we're moving about computational thinking across the curriculum. what is relation, how we install computational thinking in curricula. First of all, what is role of CT in curricula? In summary, I can say that make use of computational thinking to generate innovations from the primary to secondary education level, establishing continuum-based approach to CT development. Weave computational thinking as a part of informatics and digital skills into all subjects. And the third one, implement CT to support gender balance and foster students' creativity, paving the way to strengthen women employment in IT sectors. That we already know that we have these problems to involve more women in IT sector. Informatics in Europe, there is a huge report done in 2013, and now it is renewed some parts, but mainly there is some backgrounds about that informatics covers the science behind information technology. Informatics is a distinct science characterized by its own concepts, methods, body of knowledge, and open issues. It's emerged in a role similar to that of mathematics as a cross-discipline field underlying today's scientific, engineering, and economic progress. So this is about computational thinking, what is very tightly connected to computational thinking. Another curricula standards is from computer science teacher education from USA, the curriculum for K-12, and here we can find many also concept skills and what students should be able to, how they can use so they can learn computer science. CT, computational thinking, also should be implemented in curricula. It can be in different ways. It depends on countries, on traditions. We can suggest some suggestions come from different authors, different papers, and policymakers as well, that, for example, like make room for a minimum of 1 lesson per week for CT implementation or computer science implementation. Rearrange, increase the number of hours of math and related subjects beyond the minimum requirements to make adequate room for implementing CT. For example, like Finland is introducing computational thinking and computer science in the mathematics curriculum. Strength synergy between subjects where CT is integrated. Use comprehensive approaches for assessment of CT skills. So this is still a lot of debates about how to assess computational thinking skills. Include CT in summative assessment at the end of the lower secondary cycle. I mentioned already algorithmical thinking. Actually, algorithmical thinking is the heart of the informatics discipline, and also the, more than half occupied of computational thinking. So that algorithmic thinking is a very important part of computational thinking. And if we are going to one of papers that Barr and Stephenson from States wrote, they provided this very good table with all concepts, capabilities in and with connection with math, science, social sciences, languages. As we see this, they listed these 9 concepts like data collections, data analysis, representations, problem decompositions, abstractions, and explains them what can be implemented in computer science and what can be implemented in other subjects. From another book that's from 2018 book by Åsa Lau, who is a teacher also, Teaching Computing in Secondary School, an overview of the informatics national curricula adapted. And this is a slightly adapted schema that you see that there's three big circles, who one is dedicated to information technology, another computer science, and that one digital literacy. And in all of them, there's computational thinking, the staking part, and it's in the middle. When we are talking about problem solving, we can make different positions. For example, first one, we can think that maybe coding can be inside of computational thinking. But more authors agree that problem solving is most broader. Computational thinking is a part of problem solving, and coding is part of computational thinking, but there are more coding than included in computational thinking. And we can make this here very examples for computational thinking for pupils started from like kindergarten, from a very young age, what can be tasks, what can activities can be done, and for 5-6 age, for example, algorithmic, logical reasoning, and so on. Everywhere almost there are logics and decomposition, abstraction, evaluation. There are many activities, for example, case from Hello Ruby poster that you can see the same terms like, for example, pattern recognition, logical critical thinking, and about computational thinking. And concluding this part that we are applying many items from computational thinking. I would show this swimming pool metaphor that I elaborated. It is how to go from digital competence to informatics or computer science or computing education, that we have several components, but when we go more further to informatics or computer science education, then we need more qualified teachers, what is very important to take into account, because for these digital competencies and for like primary school, we can any teacher able to teach this. But when we are going more like elective courses like data analysis and some other courses like programming as well, we need qualified teachers. But one more thing is about knowledge transfer. There are many debates on knowledge transfer, and I would like to cite from Mark Gusal, who wrote that challenge to computational thinking is a problem of knowledge transfer. Applying computing ideas to facilitate computing work in other disciplines is clearly achievable. Applying computing ideas in a daily life is less likely. There has not been a study since Wing 2006 paper that has successfully demonstrated that students in a computer science class transferred knowledge from that class into their daily life. So there is another schema of computational thinking with coding and computer science that represent the representation. So now we are going to the more higher level, finding automatable solutions. In other words, I would say that we are now we will be talking about creating some new activities, new tasks, and solving these tasks by applying. Again, I will start with from beginning, like what Wing wrote. Actually, Wing in the first publications, she wrote about 3A, abstraction, analysis, and you see automations. That automation was already from the beginning of computational thinking. Matti Tedre and Denning in 2016 wrote a very interesting paper, The Long Quest, and they wrote that computational thinking offers very powerful mental tool for people who design computations. There is no need to make exaggerating claims, notably automatic transfer of CT skills across domains or about superiority of computational thinking over other ways of thinking and practicing. Miles Berry also wrote about getting computers to help us to solve problems is two-step process. First one is think about the steps needed to solve problem, and second one is use technical skills to get the computer working in the problem. Brennan and Resnick suggested three approaches, what I like very much, and it is we can apply in our many our problem solving. That first one is computational concepts, as I already mentioned. Computational practices, what is very important in practical applications, and computational perspectives, the perspective designers form about the world around them and about themselves. This paper was published in 2012. When we are talking about computational thinking, we can talk also about many games who develop computational thinking or include some components. We can start from very simple game, for example, NIM, that this is matches, and here is rules that start with 3 piles. 2 players take turns. In each move, you take 1 or more matches from only 1 pile. And this is a simple game, but we can start to think about strategies, who can win. And here, for example, the winning moves something, one example how can win. Here's who is taking from this one pile, another pile, and then there is some numbers and the winning position. We finish with 1-1, and who start then depends who is winning. And we can if we are thinking about number, for example, guessing numbers, there are also some strategies. For example, we can ask, is it 0 or it is 1 or 2? Is it more than some number? But this is, we can also do this with using Scratch, the same games. And another example is for example, like a Rubik cube, that we can develop algorithm, how we can just play with Rubik cube, and there is some representations of this algorithm, and also we can write a more complex program. Connections with some other subjects, STEM thinking and applying computing to automatable problems. I would like to mention what I like. This is very deep connection to mathematics education, and Polya already more than half century ago wrote a book how to solve mathematical problems, and he talked about the compositions that we now are using in our in computational thinking like engineers. This is from another Royal Academy of Engineering book, and you can see there is several components that it is interesting to read and recognize. So learning and teaching CT can be in multiple ways, and I can mention only a few of them here, like unplugged activities, also some game design, programming, integration, and the last one is a Bebras challenge on informatics and computational thinking that I would like to spend a few minutes and to present, and especially because also Taiwan is involved in Bebras challenge and doing so well. For those who don't know what is Bebras, so this is International Challenge on Informatics and Computational Thinking, established by me in 2004, and we shift from algorithmic thinking to wider computational thinking, and so there is a website, international website, and we have many countries, and we have many logos from each country, and so there is Bebras countries. At the moment there are 51 full member countries and 16 provisional member countries. Also, we have several applications this year that each year now we accept like 3-4 more countries who wanted to join our community. In last year, You know that was COVID, not so good situation, but still 56 countries send statistical data, and they manage to run Bebras challenge. And Taiwan, as you see, Taiwan is on the top of countries with almost 160,000 students. So it is a really amazing result. But I would like to focus more on Bebras tasks. That Bebras tasks are really interesting, and to educators, researchers to develop, because every year we develop original, interesting tasks with focus on computational thinking, on informatics, computer science concepts. As you see here, we have these categories of Bebras tasks, and there are many concepts that we would like to focus, and we are focusing. For example, now we have new concept like machine learning and artificial intelligence, that it's still we are shortage of tasks. Actually, we do not have good tasks in these areas. There's a few examples, for example, variable and commands, how we can make tasks on variables and commands. It is interactive. Actually, this task is interactive, that pupils can push buttons and to change these two boxes. There is another example, pattern recognition, very used for smallest children. Another task is like graph, equal graph with walnut animals, and which of the following figures can be bent back to make the figure of the dog again. And also we have some like Bebras games, Bebras cards with tasks, and in Lithuania it is quite common that in schools students make these tasks physically, that they develop and add something and adapt some different, as you see from these tasks, with some conditional statements made like physical tasks. So this is some for smallest, is in Lithuanian language, but it is still small cards about selection, sorting, and so on. And here is already that I already mentioned from about these concepts that we can make like introduce for teachers as well, and solve these tasks, and especially discuss why it is informatics, why it is computational thinking, which concepts are behind these small tasks. So Bebras methodology is based on small things, as we are talking, less is more, doing, solving, and enjoying, creating deeper digital learning culture. That is very important. And at the end of my presentation, I would just tell a few words about computational thinking in education in Lithuania, that now we focus a lot of primary school. Our primary school is grades 1 to 4, that we implementing informatics together with computational thinking in grades 1 to 4, and then that's we need a lot of resources, books, and especially we need to train teachers. And as you see here, so I wrote several books here, some books with co-authors with teachers for grade 1 and 2, for grades 3 and 4, and also methodology that we call didactical explanations for teachers, why it is, what we can learn from these tasks. And actually it is quite also related to this Bebras task, because children like to solve different type of tasks in primary schools. So summarizing my presentation, I would like to say that computational thinking is about finding automatable solutions, and this is worth doing. Computational thinking is more than the sum of its parts. The foundation of computational thinking can be laid early on. And we focus also as a in-plugged approaches and also on unplugged approaches help us in working out a solution. And the coding matters, as you saw from Simon Peyton Jones, that coding matters, but it is not the only thing that matters. That computational thinking we can teach and learn in very different ways. Computational thinking has much in common with other STEM thinking. So it means that we should think about integration, computational thinking especially in mathematics, in engineering subjects, in science, as well as in languages, and to show our students this different way of thinking and problem solving using different tools. STEM disciplines offer automatable problems. So this is also important, that in all STEM subjects that teachers can apply this computational thinking, some methods, tools, and to show how to use some tools to increase motivation of students, as well to show the power that computers can help us to see more, to find more, to get better results, to get faster results. And that is our goal, that we need to teach starting from kindergarten and in lower secondary school, upper secondary school, and also in colleges and universities. So thank you a lot for your attention about this exploring computational thinking from different angles. And in my presentation, there are a lot of information from from papers, and you can, if you are interested, you can look at the papers that I analyzed here, and actually only present here and analyzed myself, but there are really interesting thoughts, and I wish you all just to apply computational thinking in your everyday life, in your teaching your students, your pupils, and also make research, because I'm a researcher, and I encourage you also to collaborate, to make research together between countries, and including computational thinking, informatics, computer science topics, concepts, and as well we can make research on using this is Bebros challenge data. You have a lot of data. We in Lithuania, we have a lot of data from every year challenge. Have a nice day, and goodbye. If you would like to ask something me, you can write to this email address, or maybe one day we can meet in Lithuania or in Taiwan. Goodbye.